Okay, so let's talk about inverse variation. Now, inverse variation is not quite the same thing as direct variation, and in fact, it looks slightly different, but they relate in a very consistent way. Now, as a brief reminder, when we were doing direct variation had the format of y equals kx, some number times x. That was direct variation. It was always the same thing happening to x all the time. And k was the constant of variation. That's one of the things we talked about when doing direct variation. K was the constant of variation. We talked about that in the last video. So constant of variation. That was from the last video. I just want to remind you of that. So now we're still going to use this idea of k for inverse variation. However, in inverse variation, it's always going to take on the form of y equals some number k, it'll be the same number, it won't change for each problem, divided by x. So before, direct variation was k times x, well, inverse variation is k divided by x. So it means something slightly different, and we use it in a slightly different way. So they don't quite mean the same thing. But we can use them, because some situations are direct variation equations, some situations are inverse variation equations. So now, k is still going to represent some constant x. I'm sorry, just some constant. X is going to represent our input, our independent variable, and y is going to represent our output, or our dependent variable. That still does not change. That's all the same. So now, as a brief reminder as well, the graph of direct variation, looked like this. Your lines all went through the origin. That's supposed to be blue. Pretend that goes to the origin. Looks like I missed. There we go. The line goes through the origin. It can go down. That line's going up, or maybe the line goes down. That's a really steep line. That's what the graph of direct variation looks like. However, for inverse variation, the graph will always look something like this. It'll look like a curve that never touches the y-axis and it never touches the x-axis. We're only going to worry about where it is in this quadrant. We're not really going to look at these quadrants. Technically, it does exist in those other quadrants, but we don't get to that until Algebra 1. So don't worry about what it does in another quadrant for different forms of it. Let's just keep it simple. Ours is just going to be in quadrant 1. It's going to be some form of that. So here's another version of it. That's my x and y axis, just in quadrant 1. It might look like this. And it'll get really, really close to the x-axis down here. Get really, really close, but never actually touch it. So it's a curve. It's not a straight line. This is one of the only times in what we're doing in 7th grade math where our graphs won't be straight lines. This is one of those only times that's going to happen. This is inverse variation. Not quite the same thing. Now, their description isn't bad. It's just lacking a little bit, so we're gonna clarify a little bit more. Let's see what they say. And taking a quick glance at my graph I have up here. And remember that this is your y-axis and this is your x-axis. Okay, they said inverse variation is a relationship where when x increases in value, meaning as we go this way, as x increases, I'm using this example right above it, as x increases, as we go that way, it says that y decreases. Well, that makes sense. Look at the very beginning. In the very beginning, it just drops down. So y is decreasing as x gets bigger. And it says, or as x decreases, meaning this way, as x decreases, y increases. And if you watch it, that line slowly climbs and then jumps up. Didn't mean to erase it there. Now, it says the product of x and y is a constant k. We'll get that in a minute. But let's add to that original description. I think it's lacking a little bit. One of the other properties that you'll notice is that x, which is left and right, will never equal 0, meaning it'll never get to the y-axis. Because the y-axis on your graph, that's where x equals 0. It'll never happen. X will never equal 0, and neither will y. That's what that tells us. So I'm going to add that to our description. I'm going to say, I'm going to try to fit it in somewhere. I'm going to erase the direct variation. I'm going to write it right above it. X will never reach 0. It'll get really, 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 really close, like 0.00001, but it'll never actually hit 0. It'll never reach 0. And neither will y. So if y never hits 0, that means it'll never touch the x-axis, because the x-axis is where y equals 0. it'll never reach either, and neither will y. So that's a good way of adding to that description. X will never reach 0, and neither will y. Neither of them will ever reach 0. That graph will get really, really, really close to x equals 0, which is the y-axis. The graph will get really, really, really close to the x-axis, which is y equals 0. It'll get really close to where the equals 0, but never actually touch. And we'll explain why in a minute. In a lot of the situations that are inverse variation, you'll find out, oh, I could never have an input of 0 in this situation. So let's take a look at some of these examples. But before I do, I just want to point out to you, for inverse variation, the equation will always have the form of y equals some number divided by x. And that some number will be the same. We just have to find out what is that number. I want to show you some alternate versions of that equation. Some alternate versions of that equation are, I'm just going to write the same one again, right underneath it, y equals k over x. If you, let's say you wanted to get k by itself, you had to get rid of divided by 8x. To get rid of divided by x, you just have to multiply by x. So you have to multiply both sides by x. I don't really have room for that one. Times x on both sides. So they would cancel on the right side because divided by x and times by x, they're the opposites of each other, so they cancel. So on the right side, you'd be left with k. And on the left side, you'd be left with y times x, or just x times y. So x times y will give you k. So if you ever need to find k, you'll do x times y in order to get it. What we had done in direct variation when we needed to find k, back when we were doing direct variation in the last section, to find k, we would have to divide both sides by x to get k by itself. So that tells us y divided by x equals k. So for direct variation, it was y divided by x equals k. For inverse variation, it's y times x equals k. So now these are two more of your possible forms. So one of the possible forms is this one at the top, the first one we said. Another possible form is this one. And these are the two forms primarily that you'll use. You can always choose to, what if you want to get x by itself? Like for example, what if you knew y but you didn't know x? Sometimes that might happen. If that were the case, you would divide both sides by y, divided by y, divided by y. Those would cancel and be left with x equals k divided by y. So k divided by y, that would give you x. That's another alternate form of inverse variation. You do not have to memorize all these forms. If you just know the very first one, that's usually all you need because you can get what you need from it. So if you're looking for k, like if I know k, I'll plug in for y and x, and then I'll just divide both sides by x, and then I'll multiply both sides by x, and then I'll have k by itself. I'll know what k equals. So same steps as direct variation. Find k, write your equation, use it. Same steps. That's what we're going to do. So find k, write equation. I'm just going to write equate, and then solve for whatever they're asking. I'm just going to say solve, meaning do what they're asking you to do. Step 1, step 2, step 3. Same exact steps as what we did for direct variation. And we said to find k, that's going to be k is going to be x times y. So k equals x times y. And to write the equation is going to be in the format of y, y equals k divided by x. So that's what you're doing when you go to write your equation and then solve. Now let's look at example 1. That was a long explanation, but I want to make sure you knew the difference between inverse variation and direct variation. In direct variation, there was some constant rate of change, meaning it was a straight line because it always went up or down by the same amount. That's not going to be the case with inverse variation. There will not be a constant rate of change. Okay, now let's look at this example. When tickets to the picnic cost $6 each, 50 people attend. Now, when tickets are reduced to $4 each, so the price is cheaper, more people attend, meaning the lower the price, the more people are willing to actually pay the amount of money. And that makes sense. Would you rather pay $6 for a picnic or $4 for a picnic? Most people are going to want the lower price. Since we said more people, that means more people are going to show up. Complete a table and graph for prices of $10, $5, $3, and $2. Now, the first thing we have to do is we have to find k. That's the first thing we have to do. We got to find k. So now, the easiest way to find k, I'm going to not quite do it their way. I'm going to do it with less steps, hopefully less steps, is we have to find k. We said to find k, we need to do x times y. That'll give us k. If you didn't remember that, you could do the method they do, where they plug in for y, they plug in for x, And now solve for k, meaning get rid of divided by 6 by multiplying both sides by 6. They cancel on the left side, and you're left with k equals 50 times 6 is 300. You could solve for k that way. Or if you already knew x times y is k, that might be faster. So step 1 would be find k. So we look at it. We have, we already mentioned earlier, the price is what causes the number of people to show up. Because it causes it, it's what they choose. That's the x, that's the input. The number of people that show up is the output. So the dollars is the x, and the number of people that show up is the output. So now x times y, so that's 6 times 50, that will give you k. And so that gives us 300. So k equals 300. Once you know what k is, the next step was to write your equation. Write the equation. It's got to be of the format y equals k over x. It's got to be in that format. So number 2, your equation is y equals k over x. So y equals 300 over x, since k was 300 from right there. That's where we got k from. So your equation is y equals 300x. That's an equation that you're going to use for an input-output table. Make an input-output table. And they gave us the values to use for x. So our x values are going to be $10, $5, $3, and $2. Those are our x values. Our equation is 300 divided by x. That gives us y. And that'll give us our y's. So now we just have to solve for each of these. So for the first one, so for each of them, you have 300 divided by the numbers. That's 300 divided by 10. This will be 300 divided by 5, 300 divided by 3, 300 divided by 2. They chose nice, pretty numbers for us. That was nice of them. 10, 5, 3, 2. Now, if you solve each of these, 300 divided by 10, that's 30. 300 divided by 5. Well, 5 goes into 100 20 times, so it goes into 300 20 times 3, or 60 times. 3 goes into 300 100 times. 2 goes into 300, so that's half of 300. That's 150. So we now have our y values. That tells us when x is 10, y is 30. So go to x equals 10. So, and remember, x is the x-axis, the flat one. So that's going to be your cost, and your tickets is your y. So go to x equals 10 and put a point at 30. You notice that this graph goes by 25s. It goes 0, blank, 50. So that blank must have been 25. So 25, 50, 75, 100, 125, 150. So by 25s. So go to 10, go up to 30. 30 is not perfectly at 25, but it's a little above it. So we can estimate where that dot goes. It's okay to estimate when you're graphing. Now we're going to go to 5, 60. Go to 5. 5 is halfway between 4 and 6. If you chose to go by 2s down here. So it's halfway in between. And we're at 60. So go to 50. Don't go to 75, but it's somewhere in between. So it's got to be a little bit closer to 50 than it is to 75. So a little bit less than halfway, and that's going to be where 60 is at. Just estimating again. 3, 100, go to 3, which is between 2 and 4. 100's perfect down the line. So right there. And then 2, 150. Go to 2, go up to 150. It's right on the dot, so it works. You'll notice those dots are not in a straight line. But we're going to draw a curve that goes through those dots. Do your best drawing that curve. It does not have to be perfect. Just make sure that it goes through each of your points. Okay? Like just now I drew my curve by hand. It wasn't perfect, but it was pretty darn close, and that is sufficient. That will answer the question. You now have graphed. We completed a table. We made our table, and we just graphed. We did both. So we've now fully answered this question. And now if you look at the graph confirms. Look at it. That thing is not straight. That thing does not have a constant rate of change, but it does have a flow. Meaning, as x gets bigger, as we go this way, y is getting smaller and getting smaller and smaller, but it's never quite getting to 0. It'll get really, really, really close to 0, like way out here. It'll get really, 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 really close to 0, but it'll never actually cross 0. It'll just get really close. You need like a microscope to look at it. So that's what makes it, we mentioned, inverse variation. So we've confirmed, we know it's inverse variation, but most importantly, I just want you guys to realize the process is exactly the same. Other than we use a different equation when it was time to make our table. It was still step 1, find k. Step 2, write an equation. Granted, we find k with a slightly different method because we were using a different format for inverse variation. So find k and then use that different format equation to make your input-output table and graph away. Now, let's make sure this table makes sense like we said. If you have a really expensive price, let's say $100 per ticket, I think you would agree barely anybody's going to pay $100 to go to a picnic. So maybe 1 or 2 people. So at $100 a ticket, you're gonna be way out here to the right, but you're gonna be really, really low. However, someone might buy a ticket, maybe not all the time, maybe someone. Maybe it's even only every 3 picnics you throw on. Maybe if they're $100, maybe only 1 person shows up out of those 3. So maybe only 1/3 on average go to 1 picnic. Obviously, there's not really 1/3 of a person, but my point is, theoretically, you could have decimals. So it gets really, really close to 0. Or the opposite. Are they ever gonna, if they're trying to make money or pay for their costs, they're never gonna just simply put no cost for the picnic because they've got to charge something, otherwise they'll never make any money ever. So they might make it really, really cheap per person, like let's say 10 cents per person or 5 cents per person. And they did that, anyone's willing to pay 10 cents or 5 cents. So the cheaper the price, the more people that are gonna show up, the more tickets they're gonna sell. So it kind of makes sense. The lower the price, the more people are gonna show up. But they'll never actually have a price of 0 or even a negative price. You can't have a negative price for something. So this graph agrees with the things that we've discussed about inverse variation. So we're going to take a look at a few more examples and then we're going to be all done. All right, so now in this example, we're going to do question number 1 on the screen. Question number 1. So it's about painting. And I left some of our previous notes up so we can use them for reference. So in this question number 1, it says we're talking about painting. And it says the table shows the relationship between the number of days to paint a house and the number of painters. Let's say, for example, you're a contractor or you're a painting company, and you have to decide how many people do you want to hire onto the job. And you're going to base that off of maybe how many days is it going to take, maybe how many days you have to have it done. Let's say the customer says, or let's say you're inviting friends over. It doesn't have to be a business. You need to have your house painted in 3 days. Or the customer says, paint my house in 3 days. You've now got to decide how many people do I need to get here to make this happen so we can have it done in 3 days. Your goal isn't necessarily to do it as fast as possible. Your goal is just to reach the goal, to make sure that you get it done within the time limit you set yourself. So you chose the number of days. Because you chose the number of days, it is your input, it is your independent variable, it is the one that you choose. The amount of people that you end up having on the job, whether it be a business or you inviting friends over, that's going to be based on how fast you want to get it done. So now, this situation is going to be inverse, and we're going to explain why in a moment, okay? So now the question says, graph the data in the table and determine if the relationship is an inverse variation. Is it yes or no? And I already gave it away, it's going to be, but let's confirm so we can see why. Our first job is to graph everything. They said to graph at 1 day, 8 people, is what they told us. If we want it done in 1 day, we're going to need 8 people. So go to 1 day, go up to 8 people. So right here, 1 day, 8 people. 2 days, if we're going to have it done in 2 days, we need 4 people. So 2 days, we need 4 people. So go to 2 days, 4 people. So right there. Then, if we want it done in 2 2/3 days, 2 2/3 of a day, maybe a little less than 3 days, we're going to need 3 people. So 2 2/3. It's going to be right before the 3. Try to find 2/3, right about right in the middle of that. So go to 2 2/3 and go up to 3. So right about there. Then if we want it done in 4 days, we only need 2 people. So 4 days, 2 people. Just go ahead and graph it along. If you think you can finish from here, hit pause. See if you can finish all these. Now, if we want it done in 6 days, we only need 1 1/3 people. Obviously, you can't have 1/3 of a person, but they're just making a point. Theoretically, the value would be there. So at 6 days, you need 1 1/3 people, so a little above 1. Now, if you had 8 days, you're going to need 1 person. So if you look at those dots, do they go down? Because clearly it's going down. Do they go down in a constant manner? And let's see. From 1 to 2 days, it drops 4 people. Then from 2 to 3 days, it drops. From 2 to 3 days, it drops. We didn't do 3 days. We were just short of 3 days. So from 2 to 2 1/3 days, it dropped 1 more person. Now from 2 2/3, it sounds silly saying that many days, to 4 days, it drops another person, drops down to 2. So it dropped by 4, dropped by 1, then it dropped by a little bit less. So it's not dropping by a constant amount each time. Because it does not have a constant rate of change, which means it is not going to be linear. So if it's not linear, it's definitely not going to be direct variation. Remember, direct variation was graphs like this, where it goes through the origin like that, going up, or let's say it's going down. That's what direct variation looks like. It's always going to be going through or from the origin. So now draw your curve that kind of goes through these dots. Do your best to estimate where it goes. Try to just follow the curve of the dots. So now, that's my curve that follows those dots. That would be the graph of this situation. And let's see if that makes sense. Let's talk it out for a moment. If you've got almost no time to get the job done, like let's say 1 day or less than 1 day, let's say you only have a few hours, you're gonna need a lot of people and a lot of paint equipment to get that done really, really fast. Let's say everyone's painting only one wall apiece. So it's gonna get done really fast, but you're gonna have no time to do it, but you're gonna need a lot of people to get it done. That makes sense, that as we have less and less X values, or less and less days, the number of Y, or the number of people, gets really, really high. Whereas if we have lots of time to do it, maybe a do-it-yourself kind of person at home who's doing it all by themselves, or sometimes the family members aren't willing to help, if you have a lot of time to do it, maybe it only takes one person to do it, but it's going to take them a lot longer to get it done than it would take less people to do. So this makes sense with what we understand. It's just not going to be a constant rate of change because it's based off of dividing up the labor more and more. So here we had to cut the labor from 8 people to 4 people. 8 people to 4 people. We cut our amount of labor force in half. So it makes sense there almost that it went from not being 1 day, it's going to double the amount of time. And then if we were to double that again, cut that in half again, like let's say 4 people cut in half, now we only have 2 people. Well, we went from 2 days, now we're going to need double that. We're going to need 4 days. And then so it gets smaller and smaller from there. So for example, if you only had 1 person doing it, well, we were just at 4 days. 1 person's half of 2. So what's double? Almost to undo that, it's going to take even longer with half as many people. You got to double it, and that's why we're at 8 days. So it kind of makes sense, but it's just not changing at a constant rate. So this situation makes sense that it's inverse, and it graphs inverse, so you've answered all parts of the question. To determine whether it's an inverse variation, you would say yes, of course it is. Let's try another one. One quick note before I move on, I want to point out that in this one, we didn't necessarily need to follow these steps, the ones I just accidentally erased, because we weren't solving for anything. They simply just gave us the information, and our job was to plug it in and then interpret it, make sure it made sense. All right, let's take a look at question number 4 on the screen. Question number 4. We'll do one more example after this one, and then we'll be done. Now, question number 4. I still left the same tips so we can remember them if we need them. Now, let's get that out of the way a little bit more. I'm going to put it up here since we're not using that area. All right, so now question number 4. We're talking candles. It says the demand for candles at the Summer Street Fest varies inversely as the price. It's kind of like the picnic example. The more expensive the candle, if it's really, really expensive, less people are going to buy it. But if it was really, really cheap, more people would buy it. So now, inversely is the price. Mrs. Cutchin can sell 50 candles for $4 each. So make a table of the relationship and graph the data to determine how many she can sell if she increases the price to $5 each. So our job is to do like we did in that first example, make an input-output table, graph it, and they want us to solve for something. We could solve for this without using a table, just by following the steps we have up here, but we're gonna actually make the table go one step further. So that's what we're gonna do. So our first step is to find K. So our first job is find K. And we said K was found by, for inverse variation, X times Y. That will give us K. So now we were given 2 pairs of values, 50 candles at $4 each. Mrs. Cutchin is the seller of it. She determines the price. She chose what price she's going to sell it at. So she chose the $4 because that's the independent variable. Because of that, that's X. She chose that. The number of candles she sells, that's a result of the price. So that's going to be the output, or the dependent variable, or the Y. So now X times Y, so 4 times 50. So that's going to give us K. 4 times 50 is going to give us K. So remember, that was X times Y is going to give us K. Now 4 times 50, well, that's 200. So that tells us 200 equals K. So we now know what K is. So that was step 1, find K. Once we know K, we have to write our equation. And remember, all equations will take the form of Y equals K over X, all inverse equations. So if K is 200, that means our equation is Y equals, instead of K over X, it's 200 over X. That's our equation. That is the equation we're going to need in order to graph the information, in order to make our input-output table. Now, to make our life easy, I'm just going to choose easy small numbers the best I can. So for X, for the price that she's setting, we are going to try to choose easy numbers. So $1, $2. $3 might not give us a pretty answer, but we can still do it. $3, $4. I really should do that where we have more room. Oh, let me pause this. Let's get that out of the way. Okay, so now what we're going to do is we're going to go ahead. We have our input-output table. We're going to plug in each of our values. So in each of these, it's going to be 200 divided by x. So 200 divided by 1, 200 divided by 2, 200 divided by 3, 200 divided by 4. And I'm just writing the format of all these, so we can go ahead and plug them all in. 1, 2, 3, 4, and 5. And the answer to that bottom one is actually going to be the answer to the question. That's what's going to happen there. All right, so now let's answer the bottom one. I'm sorry, let's just answer each of these. So now 200 divided by 1, well that's 200. 200 divided by 2, well that's 100. I'm going to skip ahead because I'm going to go to the easy ones. 200 divided by 4. Okay, well 4 goes into 25 times, so that means it goes into 250 times. Now 200 divided by 5. 5 goes into 120 times, or 5 goes into 24 times, add a 0. So 5 goes into 120 times, means 5 goes into 100, 240 times. So 40 times. So the price was 5, okay. All right, so now, and when the price was 200, 200 divided by 3, let's see, what goes into 200 3 times? We know 6 goes into 18 3 times, so it's gonna be 60 something. So I think it's coming out to about 66 perhaps. That sounds about reasonable. So it's going to be 66 people, so I'm just going to say about 66, 67 people, somewhere around there. Gives us a value. Remember, we're just graphing, and that's not one of our perfect values. It has to be that perfect anyways. So we've got our input-output table, so let's graph each of those. Let's go to price of $1, and then we're going to put, at the price of $1, we're going to put the point they told us. So at $1, 200 people, or 200 candles. So go to $1 and go up to 200 candles. So that's at the very top. So $1, 200 candles. At $2, we're selling 100 candles. So $2, 100 candles. Stop erasing. $2, 100 candles. Now $3, about 66 candles. 66, 67 candles. If you look at our graph doesn't know the difference. It's going to be, here's about 70, 70 is about in the middle. So it's going to be closer to just under that. So try to go just under halfway. It's okay if you're not perfect. I guess I was close enough. And now for $4, we're looking at 50 candles. So go to 4, go to 50, that's halfway between 40 and 60, so right about here. 4 people, price of 4, 50 candles is about halfway. And then finally, $5, we're at 40. So at $5, we're only going to sell 40 candles, so right there. So now you have each of your dots, draw your curve that goes through each of these dots. Do your best to draw that curve. It doesn't have to be perfect, but try to make them as close as you can to where he goes through all of your points. I kind of missed that bottom one. I'm going to thicken it up so I can make it look like it fits. So like that. So that's our curve that goes through each of them. So now we've done the first part of the question. We went ahead and we graphed the data. We already made our table. Where it says make a table, we already did that on the left. So we did part 1, we did part 2. Now it says, and determine how many she can sell if she increases the price to $5. Well, our curve goes right through $5 right at 40 candles. And our table said the same thing. When we plugged in 5 down here, we got 40 as an output. And the output was the number of candles being sold. So if the price was $5, we're only going to sell 40 candles. We're not going to sell as many as if the price was only $1. And that kind of agrees with what we know. We know the higher the price, the less people that are going to buy it in general. So this was an inverse variation situation. One, because your graph was curved like this, but also because when we reasoned it out, we realized that it kind of made sense in a little bit to where we can never have a price being 0. She's never going to give away the candles for $0. So this graph will never reach $0, which will be somewhere on this line, because she's always going to sell them for something. And so because of that, it'll never touch the y-axis. Well, we hope she's in the business of selling things. She's never going to sell 0 candles. Even if the price is really, really, really expensive, she might eventually have at least one person she might be able to convince, like, oh, this must be a really nice candle, it's so expensive. Someone will at least buy it. So it kind of makes sense. So this was an example of inverse variation. So take some time to think about how this was different from direct variation. So then we're going to do one more example and we're going to be all done. All right, so in this example, this will be our last example. So if you think you can do this one for a moment, press pause and see if you can do this problem on your own. Okay, so this question is about driving. And I left those same tips up on the screen so we kind of remember the overall steps that we should be going through. So now driving. It says Ian can drive to the aquarium in 3 hours if he goes 60 miles per hour. If speed varies inversely with time, with how much time it takes you, how long will it take him how long will it take him at 36 miles per hour? Meaning how much time? And think about it, 36 miles per hour. That's slower than 60 miles per hour. So intuitively, you already know if he goes slower, it's going to take him a lot longer to get there. And so we're going to go ahead and graph this situation and then answer the question specifically at 36 miles per hour. How long will it take him? And now notice here, they're giving us miles per hour. Well, hey, that's our output. That's what happens as an effect. Oh, I'm clicking on the wrong thing. Never mind, I'm sorry. Ignore what I just said. I'm reading it backwards. Miles per hour, that's going to be how many our speed and then our time. So how fast we're going, okay, that's your miles per hour, and then we got to figure out how long it's going to take. So they're telling us at what output. So what I was saying was actually kind of right. If it's going to take us 36 miles per hour, if we're going to go that fast, I'm sorry, if we're going to go 36 miles per hour, I keep saying this wrong, how long is it going to take us? All right, so if you think you got this one, press pause, see if you can do it. Now, we're going to follow the same steps as always. We're going to start by finding k. So now to find k, it's x times y. So now, here's what we have to look at. A lot of us would think, well, hey, you almost choose how fast you're going to drive, but really, sometimes you can't, like in traffic and whatnot. So this is almost an opinion type question. But if you look at your graph, use that as your hint. Time is down here, left and right, so time's going to be x. That's going to make your speed your y. But in other words, you also could ask yourself, what if I have 2 hours to get there? How fast do I have to go? Or what if I have 8 hours to get there? How fast do I have to go in order to get there in time? So think of it that way. So we're choosing the time. We're choosing how long do we have to get there. Oh, that's not a good way to do your traveling. You really shouldn't be like, I have 2 hours to get there. I must go 120 miles per hour. That's a terrible idea. But we're just doing this in a theoretical sense. Maybe it's a race. Hopefully not out in public. Moving on. So find k. X times y. So according to this, time is our x. Time is our x. So that means that 3 hours, that was x. And then the speed was 60 miles per hour. That was the result of that, according to our graph. We're saying we chose the time. The speed is the result. It's the output. So now x times y, that's going to give us k. So that means 3 times 60 will give us k, because that's x times y equals k. If you forget why it's this, go back to where we first explained why it's x times y will give you k. So now 3 times 60 is 180. So that means 180 equals k. So we've done step 1. Step 1 was find k. We've now done that. So if you had trouble up until this point, maybe hit pause, see if you can take it from here, if you haven't done so already. Now make an input-output table. So at different times, that's what we're going to do. We're going to make an input-output table. So I'm going to use strategy. I'm going to try to pick numbers that might be easy to divide to save us time. So let's see. For x values of 1, 2, 3, 4 might not be pretty. 5 will be. So I'm going to go to 5. I don't think 4 will be an even number. Oh, no, it will be. So let's get 4 in there. Hopefully it will be. 4, 5, 6, and I think that hopefully might be enough values to get us going. So let's use each of these values. That's probably way more than you need. But remember, you are making a curve though, so the more the better. The more defined your curve will be. And our equation, oh, I forgot step 2. Write the equation. Well, if we know k, we can write our equation. Our equation is going to be y equals 180 over x, because it's k divided by x. That's our equation. So 180 divided by x. That's going to be our equation. And then that will give us our y. So now I'm first just going to take a moment to write all these in. 180 divided by, for each of them. I'm going a little sideways so I can fit it. All right, 1, 2, 3, 4, 5, and 6. All right, so 180 divided by 1, well, that's 180. 180 divided by 2 means cut it in half, that's 90. 180 divided by 3, when we did that up here, we multiplied originally, that's 60. 180 divided by 40. Well, I know that 4, I know 40 goes into 16, which means 40 goes into 160. 180 minus 160, that's 20. So 4 doesn't go into 20, it goes into 5 times. So we know 4 goes in 160 40 times, and it goes into 25 more times. So that means 45 times. A grand total of 45 times. If you don't like doing that mentally, you don't have to. That's just kind of maybe a way of organizing it. 180 divided by 5. Well, 10 goes in 180 18 times. 5's half of 10, so it's going to go in twice as many times. So twice of 18 is 36. So 5 goes in 18 36 times. And then 180 divided by 6, well, we did that up here. So that's going to be 3. So we've got each of our values. We now have ordered pairs that we can graph on our graph. So so what we're going to do is when x is 1, well, hey, y is also 1. So if you only have 1 hour, you've got to go, wait a minute, that doesn't quite make sense. Let's see if that's a reasonable answer. 180 divided by x. So 180 was k. X is going to be how much time we're choosing, and y is going to be how fast we need to go. So if we have 1 hour of time, and we are going to go 180 divided by 1. Oh, that's why I can't divide. That was my mistake. See, that answer wasn't reasonable. That's what I mean by make sure your answers are reasonable. I was about to be like, wait a minute. If we go 1 mile per hour, we're going to be able to go how far we need to go in by going 1 mile per hour. That didn't make any sense. That answer wasn't reasonable. Especially when we expect our graph to be curving like this. So we're expecting this answer to be somewhere up here, up high. So that wasn't a reasonable answer. So that's what I mean by making sure your answers are reasonable. So let's try this again. 180 divided by 1. For those of you paying attention or wondering, what is this guy thinking? That's 180. I'm sorry for that mistake. Anyways, 1 hour, go up to 180. Well, unfortunately, that's off of our graph. I'm going to estimate 110, 120, 30, 40, 50, 60, 70, 80. All right, so that's going to be somewhere up here. It's not perfect, but somewhere up there. Now, it's okay if it's off your graph. I normally just would not use that point, but just for fun, I'm throwing it up there. So 2, 90. So go to 2, go up to 90, put a dot there. Now 3, 60. Go to 3, go to 60. So that means if you got 3 hours, you go drive 60 miles per hour. 4, 45. If you've got 4 hours, you got to drive 45 miles per hour. Somewhere between 40 and 50. 5, 36. So if you have 5 hours, go up to 36. 36 is a little more than halfway between 35 and 40, so a little more than halfway if you can do that best you can. And then if you have 6 hours, you got to go. Oh, that's a 30. 30. So that's what I mean by the reasonable answers that happened again. So 30. So if you have 6 hours, you got to go 30 miles per hour. Now you've got enough here where you can kind of see the curve going on. You could plug in more if you wanted to. I think just to plug in an easy number, I'm gonna choose 9 because I go 9 goes in 18. So 180 divided by 9 is going to be 20. That way we just have one more data point. So at 9 we're at 20. That way we have a little bit more shape of our curve. So now draw your curve through those dots. Do the best you can. Try to get through each of them. And make sure your curve starts to level out. So that's our curve. So we've now graphed it. We've now followed that first step where it said to graph it. So make sure your version of it looks similar to this. And now to answer the question, how long will it take them at 36 miles per hour? Well, 36 miles per hour, it's somewhere in here. Which means it looks like it's somewhere around here. But if we actually look, wait a minute, we actually had 36 miles per hour as one of our outputs. So if we're going to have an output of 36 miles per hour, if our goal is 36 miles per hour, it says how long is it going to take us? It's going to take us 5 hours on the dot. So if you follow the graph, it looks like it's close to 5 hours. But if you look at your input-output table, it's exactly going to be 5 hours. So that worked out pretty good. So now this is just one last example of inverse variation. So if you guys just remember, it's not quite the same as direct variation, but it is going to give you an opportunity to graph some different scenarios in life where things aren't always directly proportional. Maybe they're sometimes working with extremes. So the steps are the same. One final recap. You're just like direct variation. You're going to find x first. Once you find x, you're then going to write your equation, and after that, you're going to do whatever you need to do with it. Make an input-output table, or maybe solve for just one value. But just whatever you do, take your time. This is one of the only sections we'll do to where our graphs will not be in a straight line.